Okay, today we're going to look at pendulums. All right, it's very similar to springs. You'll be shocked how similar it is. Okay, so a pendulum is essentially it's a mass. We often call it a pendulum bob. I'm not sure why. That's hung from a fixed point, usually on a ceiling or some elevated place, on by a string or a rope, and it can swing freely back and forth. I'm not very good at keeping it can swing freely back and forth. We call that a pendulum. Okay, now a pendulum, like a spring, has an equilibrium position, and that is the position where it will not move if it is released in that position. That's because at that point the restoring force is equal to zero. So when a pendulum is hanging vertically, 90 degrees to the ceiling, then the restoring force is zero, so it doesn't accelerate, and it will not gain any kinetic energy or and it has no gravitational potential energy that it can release. So it has no mechanical energy in this position if it has not been displaced from equilibrium. Now, if I displace it from equilibrium, just like a spring, it's going to gain potential energy, which will then convert into kinetic and back into potential in an oscillating fashion that is undergoing simple harmonic motion. So, um, like with the spring system, there is a restoring force, and in order for it to well, let's just say this. What is the restoring force? Well, this restoring force, you won't be surprised to learn, is equal to mg sine theta. So if I displace this 1 degree, then mg sine 1 is the restoring force pushing it back this way. If I displace it to 2 degrees this way, then mg sine 2 degrees is the restoring force pushing it back towards equilibrium. Now, in order to experience simple harmonic motion, it is a criteria that the restoring force has to be proportional to the displacement from equilibrium, and that's true with pendulums. But it works really well when the angle is small, like say 10 degrees or so or less. When we start getting above that, what we find is that I keep changing my displacement, but the restoring force isn't going up as much. And we'll get to that later. But it's just worth noting that really the simple harmonic motion aspect of pendulums is pretty much mostly relegated to just those small angles. So let's just take a look at what I mean. So if I take a 10 kilogram pendulum bob and I displace it at an angle of 1 degree, that's not very much, the restoring force is going to be 100 because 10 times 10, that's mg, times sine of 1. I have 1.74 newtons of restoring force pushing it back towards equilibrium. If I displace it 2 degrees instead, and by the way, we typically measured the displacement of a pyramid, the amplitude of it, in terms of degrees. If I displace it 2 degrees, I find that I'm going to get 3.48, which, by the way, happens to be double this, pretty close to it, okay? If I displace it 3 degrees, I find the restoring force is this, which happens to be 3 times this one, and so on. If I displace it 4 degrees, I get this value, which is 4 times that value. So the restoring force is directly proportional to the displacement as measured in degrees for these smaller angles. We're going to find we get to larger angles, it quits working so well. I mean, it still works pretty well. It just doesn't apply to this one equation we want to use. But before we get to that, let's just talk about how we're going to determine the period of a pendulum. So the length of a pendulum is something that students sometimes mix up. You do not measure it from the pivot point to the top of the pendulum bob. You do not measure it from the pivot point to the bottom of the pendulum bob. You have to measure it to what we're going to later in the year call the center of mass. So for a spherical pendulum or some sort of geometrically uniform object, it's going to be the center of the object that we want to measure from. Okay, so that's the appropriate place to measure the length of a pendulum. It's going to be important when we do lab work today. Now, the period is the time it takes to complete an oscillation, just like it was with the spring. But the difference is here is the time it takes to get from maximum displacement across equilibrium and back to their starting point. So in this case here, I'm going to count Mississippis. 1 Mississippi, 2 Mississippi, 3 Mississippis. This is a 3-second uh, uh, period to this one here, roughly. Now, the amplitude of a pyramid is something we're going to measure in degrees. All right. So instead of measuring in centimeters, we're going to measure it in degrees. It's just a more effective way of measuring that. And so now we get to the period of a pendulum. The period of a pendulum is very similar, should look really similar to what we saw yesterday with springs. So the period of a pendulum is equal to a constant 2 pi, just like yesterday, times the square root of a fraction, just like yesterday. But in this case, the length is the longer the L is length and G is gravitational field strength. So if the length increases, it's going to take longer for the pendulum to complete a path. And if the gravitational field strength is stronger, it's accelerating faster. It's going to take it less time to complete that. So we said before, small angles are used when doing this. As long as that happens, it doesn't change the. So if only small angles are used, then changing the amplitude doesn't change the period. So in other words, if I take it from 1 degrees to 5 degrees, well, the restoring force got greater, so it's going to accelerate faster. Even though it's going a greater distance, it's going to accelerate faster. We find it doesn't change how long it takes to complete a swing, just like it didn't with a spring. So displacement doesn't figure into my period equation because it does not affect how long it takes to swing, which is kind of a weird thing. The first guy who figured this out was Galileo, actually looking at a chandelier in a church. He noticed that at the beginning of the service, it swung a long way in a certain amount of heartbeats. That's what he had. And at the end of the service, it was still swinging, and it still took the same number of heartbeats, but it's going a much smaller amplitude of swing. Anyway, well done, Galileo. So because gravitational mass is equal to inertial mass, changing the mass is not going to affect the period either. So in other words, if I have twice as much mass, I'll have twice as much restoring force and twice as much inertia, and therefore it's not going to accelerate any fast. The acceleration is not going to be any faster because I've doubled both the gravitational uh, force on it, but I've also doubled the inertia of it. We've seen this a million times this year. So notice mass is not part of this equation. It doesn't figure in. Now, if the angle gets larger than 10 degrees, what we find is that the system is still going to oscillate back and forth. It's still going to convert mechanical energy from the form of potential energy to kinetic and back to gravitational potential. However, the period equation is going to work because the acceleration is going to become closer and closer to being limited to pretty close to G when it gets up to here. And down here, that's not the case. So we find that it tends to get stuck at a certain value up here. But that's not really going to figure in very often. Last thing is, let's just talk about what is it that the amplitude does do. It doesn't change the period, but it does change the potential energy and therefore the mechanical energy of the system. So we've got to get used to this equation here. So if a pendulum has length L and I displace at a certain number of degrees theta, how much potential energy did it gain? Well, what it gained was L. Basically it got lifted this high, right? So how high did it get lifted? How much potential energy did it get gained going from here? And remember, with conservative forces, the path doesn't matter. It doesn't matter if I went straight up or I followed this arc, right? And gravitation is a conservative force. So in going from here to here, I basically went this high. How high is this? Well, it is L minus this length here, and this length here is going to be L times cosine theta. So L, this length, minus L cosine theta gives me this amount of vertical displacement. So if I want to figure out how much potential energy a pendulum has based on its amplitude, I would say it's going to be equal to mg times L minus L cosine theta. Now, just like yesterday, I can find the period of a pendulum by measuring like how long it takes to complete an oscillation. So just like yesterday, I say, oh, well, here's maximum displacement. Now it's completed an oscillation. That took 2 seconds. Once I know the period, then I can apply that equation, right? So if I know that, I could say, well, I know what G is. I'm on Earth, right? So I can figure out what the length of my pendulum is just by measuring the period and knowing what G is. On the other hand, what if I took it to a different planet? Okay, if I took it to a planet, then I could figure out what G is on that planet because if I know the length of the pendulum. All right, listen, thanks for watching, and I'll let